they'll just have to fill in those blanks for themselves. The work is pretty good, though, I think, right? Pretty thorough. We did a good job. Okay. Sorry, those of you that are watching from home, that this cuts in the middle of an example, but like Mr. Kulik forgot, and you just have to deal with it. It'll be okay. You haven't missed any content, just questions. And then that, Katie, you could punch those through, right, to the end to get what you're looking for. Yeah. No big deal then, right? Tricky, though. Tricky with the variables and like, this has 3 variables. How am I going to do 2 equation system with 3 variables? How do I solve that? That's the trickiest part to it, is realizing that like you're looking for R2 minus R1. So like, I think that's the sneakiest one in the set there because of that little aspect. Okay, anybody else? Cool beans, daddy-os. Let's get rocking then. So last time we finished section 2.1. Am I correct on that?
Yes.
Okay. Let's do 2.2 then. Oh, no, 2.2 is not standard position angles. That's 2.3. Don't get ahead of yourselves, Mr. Kulik. All right. So 2.2 is trig functions on acute angles. So if we go back to geometry, and we did like sine of x, cosine of x, tangent of x, where did these x's have to come from? In geometry, if I did sine of x, cosine of x, tangent of x, where did I have to get those x's from? Angles. What kind of angles?
Like in a right triangle.
Okay, angles from a right triangle. More specifically even than that, they had to be acute angles from a right triangle. You couldn't use the 90 degree. Okay, so let's just say that I have some nice friendly right triangle. So that is a lumpy looking triangle. Call this angle here theta. Relative to that angle theta, this side in yellow we would call adjacent. And this side in green we'll call opposite. And this side in blue we'll call hypotenuse. So if we use our acronym SOHCAHTOA, we should remember that sine theta is opposite over hypotenuse, that cosine theta is adjacent over hypotenuse, and tangent theta is opposite over adjacent. I think everybody does that much, at least in their geometry class, right? Now you might ask yourself, well, Mr. Kulik, we have 3 side lengths, opposite, adjacent, hypotenuse. And we're going to make a ratio that involves 2 quantities, right? If I'm picking any 2 quantities out of 6 to form a ratio, or I'm sorry, any 2 quantities out of 3 to form a ratio, shouldn't they give me 6 possibilities, not just 3? Why couldn't I have like hypotenuse over opposite, or hypotenuse over adjacent, or opposite, or adjacent over opposite? Right? You ever wonder why not? The answer? Those are things we just didn't tell you back in geometry. Maybe. Some of you, maybe we did. So they have names. Let's see what their names are. The first one, cosecant theta. Is equal to hypotenuse over opposite. The next one, secant theta is hypotenuse over adjacent. And the last one is cotangent. Hi.
Hello.
How are you?
Good, how are you?
Good. Tessa, you got yourself a get out of jail free card here. You're welcome, dude. All right. So at this point, you might be going, oh, crud, Mr. Kulik. Does this mean like I need to memorize like a whole new acronym to remember these ones? I mean, you could, but not really. Do you notice a relationship between the ratio for sine and cosecant? What is the relationship? They're reciprocals. Yeah. How about cosine and secant? Reciprocals. Tangent and cotangent? Reciprocals. So, if I remember SOHCAHTOA, I don't have to memorize these new ratios. All I have to memorize is which ones are reciprocals of sine, cosine, and tangent. Does that feel okay? Now, hopefully, it'll be easy to remember that tangent and cotangent are reciprocals because they both have the word tangent in them. Anybody think they'll have a problem remembering that? No, that's usually pretty easy to remember. So, the only thing that we're left to worry about is remembering whether cosecant goes with sine or cosine, or secant goes with sine or cosine, right? Everybody's cool with that? The way I remember it is no cos go together. So cosine does not go with cosecant. The only choice I have left for it is secant. And because cotangent and tangent went together, the only choice to go with sine is cosecant. So that's how I remember it. So I don't really need to remember all these new ratios. I just remember SOHCAHTOA and then which ones are reciprocals of which ones. Everybody cool with that? Let's practice using these. Okay. Yeah, I'm going to write it. I'm going to draw it this way. So it matches my picture and I don't do something stupid. All right. So what if we ask you to draw the 6 trig ratios and we give you this triangle? First thing you should know about this triangle is, okay, it's a right triangle, yes. Should note that first, that we are using a right triangle. What else do you notice, though? Is it missing some information? It's missing a side length. Oh, no. How do I find that side length? Pythagorean theorem, which is? Great. When using the Pythagorean theorem, what do I have to be careful about? Yeah, c squared must be the hypotenuse. All right. In this situation, the hypotenuse is what I'm looking for, so that's easy enough. So I get 29 as c squared, or the square root of 29 as c. Everybody okay with that? All right. So sine theta should be five over square root 29. Now, do I love the way that looks? No, what should I do? Excellent. That process right there is also known as rationalizing the denominator. Quick, in your heads, what's the square root of 29 times square root of 29? Good. Cosine theta should be good. 2 over square root 29. Got to do the same thing. I'm not going to show the work that time. Is everybody okay with me skipping the rationalizing the denominators work? I hope so, right? You guys should be like, that's pretty shrug worthy. I ain't worried about it. Tangent is 5 over 2. Everybody's cool? Feels good? All right. Let's do the other 3. Cosecant is great. How'd you do that so fast? You looked at the reciprocal of sine, but sine is this. No, you were smart and you looked at the at part. Why did you look at that version instead of the final answer? Yeah, it avoids getting that square root in the denominator by taking that piece, right? Yeah. Good, 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 good. Secant is square root 29 over 2, doing the same thing, right? And then cotangent is 2 over 5. Is everybody happy with what we did there? Pretty easy, right? We're just using some definitions. No big deal. Very light on the math. Okay. What if we have this situation? All right, let theta be an acute angle in a right triangle if sine theta is equal to 1/3. Find the other 5 trig ratios for theta. First thing I should do is draw a picture. That picture should look like a right triangle where one of the acute angles is theta. Does it matter what your picture looks like? As long as it's a right triangle, it doesn't matter how you orient it. Does it matter which angle you pick theta to be? No, as long as you're consistent is like after that name theta, or after you name your theta, you name the opposite adjacent and hypotenuse accordingly. Everybody's cool? What does our triangle need now? Side lengths, right? We need some side lengths. How am I going to figure out those side lengths? I'm going to use that sine theta is 1/3. What side lengths can I get from that? Opposite and hypotenuse. The opposite should be 1. The hypotenuse should be 3. How am I going to get that third side? Pythagorean theorem. What do I have to be careful about? C is the hypotenuse. Plugging into A, I'm going to put A 1, or you could leave it as A. B should be the 1, or you leave it as B. And C should be the 3. So I get B is equal to the square root of 8. What do you notice about the square root of 8? You can simplify that, right? Do you remember how to simplify radicals? You're looking for factors that are perfect squares. So what factor of 8 is also a perfect square? 4. So I can just think about the square root of 8 as the square root of 4 times the square root of 2, or 2 root 2. If you could do that in your head, that's perfectly fine. But these are notes, so I'm just kind of talking through reviewing how to do this, because some of us may be very natural still, and some of us may be, oh, I kind of remember that, but not so great. So this side is 2 root 2. All right. We already know that sine theta was 1/3. We still need cosine theta, so that should be 2 root 2 over 3. Everybody good there? Tangent theta should be 1 over 2 root 2. Uh-oh! Ay. Leave me alone. What do we notice? Yeah. How do we rationalize this one? What do I multiply the top and bottom by? Just root 2 is the easiest. It's not wrong to do 2 root 2, but then you have some reducing you need to do. All I need is the radical part. So again, that 2 is that 2, and root 2 times root 2 just gives me regular 2. Just to reiterate where everything's coming from, because there's a lot of 2's rattling around down there. Everybody feel good? So doing all right. Cosecant should be 3. Secant theta should be, can you do it rationalized in your head without having to write anything down? 3 root 2 over 4. That's correct. Again, we just skipped some steps and did it in our head. If you can't see it, write it out. It'll become obvious pretty quick what happened. Cotangent is 2 root 2 over 1, or just, I'm not writing over 1, I'm just going to write 2 root 2. No sense in writing over 1. It's not wrong if you do it, but I mean, like, I'm going to skip it. What do you guys, so far so good? All right. Next up, what if I ask you to do the sine of 30 degrees without a calculator? Oh no! Is this really an oh no? All right. Well, let's start by drawing a picture if we're not sure what to do, if it's an oh no situation. So there's my right triangle with a 30 degree angle in it. What else can I say? The other angle is 60 degrees. Okay. Wait a minute. What are the angle measures here? 30, 60, 90. That rings a bell from geometry, right? Wasn't that one of our special right triangles? Oh, yeah. What are the ratios of side lengths for a special right triangle? Or 30, 60, 90 for special right triangle is, Chanel?
So 2 is the height, the hypotenuse. 1 is the taller one, and then the one.
The short side.
Yeah, the short one, and then the one with root 3.
Mm-hmm. Yeah. So again, I think short side x, middle side x root 3, long side 2x. If I look at the coefficients on each of those x's, the smallest coefficient goes on the shortest side, the middle one goes on the middle side, the longest one goes on the longest side. Right? Root 3 is like 179 or something if you decimal it out. Or close enough. All right. Great. So if I do SOHCAHTOA now, opposite is x, hypotenuse is 2x. That reduces down to 1/2. All right, Mr. Kulik. Hey, this 30, 60, 90 triangle business, is that something I should remember? Yeah, it'll become quite useful in about one more lecture. Speaking of special right triangles, was that the only one?
No, 45, 45, 90.
Yeah, there was another one, the 45, 45, 90. Excellent. What were the ratio of side lengths there? This is easier because it's an isosceles triangle also. So two of the little side lengths are the same. The legs are x, and the hypotenuse is x root 2. Is that another good one to remember? Yup. Okay. What if I ask you to find sine of 17? Yeah, notice there's no special directions here. 17 doesn't appear in any of these special right triangles. What am I going to do with that? Well, the answer is use your calculator. Before I type this into my calculator, what's the first thing I should check? I want to check the mode. I want to make sure I'm in degree mode. To check the mode, we press the mode button right next to the blue second command. My calculator is already set in degrees. If yours wasn't in degrees, use your arrow buttons to move down until the degree is highlighted and press enter, and that'll stick highlighted. Once you're done with that, press second in mode to return back to the main screen. Then we can just type sine of 17. So I get about 292. What if we wanted to do, say, secant 78? Oh, Mr. Kulik. Jacob, what's up? Certainly. Sure. If I look at my calculator, what do you notice? No secant button. Oh, no. Whatever should I do? Janelle.
1 divided by the cosine.
Yeah. Again, we remember that secant is the reciprocal of cosine. So I could just write it that way. So when I type that into my calculator, I could use the fraction command, alpha y equals option 1, and write it like a fraction. 1 over cosine 78. That's fine. I could just use division, do like 1 divided by cosine 78. That's fine. Or if I'm feeling fancy, I can do cosine of 78, and then I can do the x to the negative 1 button to make the reciprocal. That's fine. Notice they all gave me the same answer. What do I want to be careful about when I'm doing that last option? Is you got to make sure that you close your parenthesis, because if you forget to close it, it's going to do the cosine of 1 over 78 degrees, which is not the same thing as 1 over cosine of 78. Everybody's cool with that? So what do we get? About 0.81, or I'm sorry, 4.810. Everybody feeling good still? Any questions so far? Good. This is all pretty basic stuff. But it's important to remember where we started, because we're about to break out of the shackles of the right triangle here. All right, last example in this section. If I ask you to solve the triangle, what am I asking you to do? All the side lengths and all the angle measures. Does it matter which order we do these? It doesn't. What do you want to start with? Angle, okay? I'm going to call that angle x. How do I find that angle?
Angle summation theorem.
You know the angle sum theorem, triangle sum theorem. So I should write 180 minus 90 minus 41. Right? Note, you could also use the corollary to that, which is just 90 minus the acute angle. It's the same thing. Either is fine, though. I like the corollary because it's less subtracting. But that's me. It doesn't matter. Which one do you want to do next? The leg or the hypotenuse? Hypotenuse, great. I'll call that y. What are we going to use to solve for y? Cosine, great. Relative to the acute angle, We know adjacent, and we're looking for hypotenuse, so that means cosine. Could have used secant here. Yeah, but like, why would you? It's just like, just a bigger hassle. All right, solve for y. We just multiply both sides by 12. And it's calculator time. So, oh my goodness, Mr. Kulik, what did you do? What did you do? It's adjacent over hypotenuse, dummy. Well, you don't have to be mean about it, but yeah, that's a pretty dumb mistake, Mr. Kulik. It's the end of the day, guys. Sorry. I had all my classes today. It's a lot. You know, like you've been talking for like, I don't know, like 7 straight hours or something. Pierce, what's up? Absolutely. Say hi to the other guys while you're there. It's a pee-pee party. Or maybe it's a poo-poo party, I don't know. All right. The last one we'll call Z. What do we want to use to find Z? Great, that's the best option. Note that you could use also the Pythagorean theorem. You could also have used sine. What's the drawback of using either sine or the Pythagorean theorem? You could be wrong because your previous answer is wrong. Assuming your previous answer was correct, though, there's still a drawback to doing it. It's that you're using a rounded answer. So there's like a little bit more inaccuracy involved. Now, for you guys and what you're doing, if you're rounding two decimal places, do you think it's going to matter? No. If you're working for NASA and you're trying to land on the moon and like the decimal point to the 100 places matters, yeah. So I just want to make mention that like there is a better way to do this, which would be using tangent because you have no rounded inputs. But the other ways you could have done it that we just mentioned were fine. You would not be graded down for those. But I do want to make mention that like if you can avoid using a rounded answer, it's good practice to do so. But you wouldn't, you know, like in this class, there's no problem with it. So 1043. Right? If we use a rounded answer and then round again, it's like rounding twice. You know what I mean? If you become a statistician or a scientist, that now starts to matter, right? If you do a calculation where you round twice inside the calculation instead of just once, that matters now. Okay. 2-2, any questions on this? Pretty standard stuff, right? Looks a lot like the Delta math practice that we did at the beginning of the year. That's because it's still the same stuff. All right. 2.3 is about angles of rotation. All right, let's go back in time to geometry. What's the biggest angle you could draw in geometry? 180 degrees, right? That's okay, because if you try to draw something like this, where do you measure your angle? Always this side, right? You would never go with the bigger one. Everybody agree with that? So this is frowny face in geometry land. This is happy face in geometry land. So you can only do angles from 0 to 180 degrees, right? In geometry. That's the only pictures you can draw. Yeah, well, that seems inadequate. Let's see if we can do better. So, this method that we're going to use now to draw angles is called the standard position form of an angle. We're drawing an angle in standard position. It all kind of means the same thing. I'm going to abbreviate standard position as SP quite frequently. So this is how we're going to draw a standard position angle. Okay? If I'm using, let's just take this guy that we had from before. We have the vertex of our angle. I'm going to call one side of the angle the initial side, and the other we'll call the terminal side. And I'm going to translate this angle onto the XY axis so that the vertex is at the origin. The initial side is on the positive x-axis. And then the terminal side will be wherever it lies. That looks terrible. Everybody's okay there. And what we're going to do to measure our angles, we're going to imagine rotating our terminal side, starting at the initial side, counterclockwise to its location. We're not in geometry. This is not the geometric method of measuring an angle. This is now the standard position method for measuring angle. What's the advantage here? Is we've now created a method where we can measure angles up to what size? 360, it seems like, right? Now notice that when I did this, I said we're going to rotate counterclockwise. Why not go clockwise? Well, there's no good reason we can't do counterclockwise. So let's use counterclockwise to represent something else. Let's do positive angles counterclockwise. And regular old clockwise will be the negative angles. So now what can we do? Negative 360 to 360, right? Everybody agree with that? But wait, we're not done. Now, you initially, or all naturally, wanted to stop at 360, but why? Why? Skiers, snowboarders, skateboarders in the room. A 540, what's that trick look like? It's like 1.5 turns, right? So if I was doing a 540 degree angle, we start at our initial side, we'll go one full time around, and then another half around. Can we call that a 540? Yeah! We can do that still, right? There's nothing that restricts us from going around more than once, spinning our terminal side more than once. Oh, all right, Mr. Kulik. So now what size of angles can we make? All real numbers. Negative infinity to positive infinity. All we need to do is keep spinning until we get there. This is a big deal. We've done a lot here in just a few minutes. This was a very clever idea, the person that came up with this. Let's just note a comparison here. If I graphed 180 degree, or I do the standard position for 180 degree, what do you notice when I compare that to the 540? What do you notice when I compare these two? They're at the same point. I don't think that makes sense, but I know what you mean. You mean the initial side and the terminal sides are in the same positions. Are they the same angle measure? No. But their initial and terminal sides are identical. If you stripped away the rotation marks, could you tell the difference? No. We're going to have a name for these kinds of angles. We're going to give these angles a special name. They're called coterminal because their terminal sides are in the same position. So coterminal angles have different angle measures, but their initial and terminal sides are identical. Hi, Miss Lytle.
Your daughter has a fever of 101.
Okay.
Joss is getting you a sub right now to come down. I think it's just going to be Yannick.
Okay.
So you need to back up.
Okay.
Kathy told me to tell you.
Okay.
Thanks.
You're welcome. I guess I'm leaving in a few minutes. So it appears my daughter has a fever, so. What I'd like for you guys to do without me is, this was actually like the very end of 2-3 anyways. There's like one example of finding like some coterminal angles. Just real quick, how would you, if I gave you an angle measure and asked you to find an angle coterminal to it, what would you do? Add or subtract 360, right? Each time you do that, you'd get a new coterminal angle. So you could do as many times as you wanted. Each time you do it, you're going to get a new coterminal angle. If it was in radians, what are you adding and subtracting instead of 360? 2 pi. Okay? They know that because 180 degrees was pi in section 2.1. That was our conversion factor. So 360 should be 2 pi. Plus, they did this probably from the integrated class, would be my guess, as why they came up with that so quickly. So that takes us up. We did 1 through 24 was the homework last time. 25 to 44 will be the new stuff. And we'll finish 2.4 next. 2.4 is the last section in this chapter. We'll finish that next time. Given the situation that we're finishing the chapter next class, what haven't we done yet this chapter? Homework quiz. What might you be expecting next class? Homework quiz. What would it be on? Yeah, up to 2.3 at maximum. Okay, we'll do questions first. But up to 2.3. So that's through problems 44. Okay. And since we're going to be finishing section 2.4 next time, what's going to be happening soon after that? Test. Now, is that a good thing or a bad thing? You should think that's a good thing, because what that means is the test is going to be very narrow. Right? If we haven't done that much, it can't be that wide-ranging. The questions will be very narrow. It should be easier to prepare for. Right? The last chapter had a bunch of sections. There's a lot of stuff to go over. That should have been more of a problem than like a 4-section chapter that's like, and what have we done here? One of the sections was even straight review from geometry. Right? There's really 3 new sections in here for you, and some of them are pretty straightforward. Okay? You guys should spend the rest of your time working on some of this stuffs. Okay?